Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Vector Differentiation from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. First, simple differentiation of vector with respect to scalar like time is discussed. Next, the description of a curve in space is given and the concept of curvature and radius of curvature is discussed. Third, the kinetics of motion of a particle in vector form is discussed. Fourth, derivative of a vector with respect to space coordinates, the gradient, has been introduced. Geometrical interpretation of gradient is also discussed. Properties of the gradient both as differential operator and a vector as given. Related differential operators of divergence and curl of a vector and the Laplacian operators are described. Lastly, the product rule when the gradient, divergence and curl of more than one scalar or vector function is involved are written down. Now let us see differentiation with respect to a scalar. Differentiation of a vector with respect to a scalar is akin to ordinary differential equations of a function of one variable. Consider a vector A, that is function of a scalar t, which may often but not necessarily be time. In general, a change delta t in t will lead to a change delta a vector in a vector given by delta a vector equals to a vector as a function of t plus del t minus a vector as a function of t. If the vector delta a vector over delta t approaches a limit as delta t tends to 0, the vector a as function of t is said to be differentiable and d a vector by dt is equals to delta t tending to 0 delta a vector by delta t. It is the derivative of a vector with respect to t. D a vector by dt is equals to limit delta t tending to 0 delta a vector by delta t is equals to dax by dt into I cap plus day by dt into j cap plus daz by dt into k cap. Usual rules of differential calculus are applied here. That is, d of a vector plus b vector by dt is equals to d a vector by dt plus d b vector by dt, and d a vector dot b vector by dt is equals to d a vector by dt dot b vector plus a vector dot d b vector by dt, and d a vector cross b vector by dt is equals to dA vector by dt cross product with b vector plus a vector cross db vector by dt. Notice that order of the two vectors in the last equations must be preserved. Sometimes more useful to write in terms of differentials rather than derivative. For example, the locus of the tip of unit vector r cap is the surface of a sphere of unit radius, and on taking the differential of r cap is equals to 1. So r cap dot dr cap plus dr cap dot r cap is equals to 0, which implies that r cap dot dr cap is equals to 0. Hence, the increment of a unit vector is always perpendicular to the vector. Curves in space. The simplest way to define a curve in space is through parametric representation. So, let r vector dependent on t, the position vector of a point P in space with coordinates x, y and z, be a function of some parameter t which may or may not refer to time. Then r vector t is equals to xt I cap plus yt j cap plus zt k cap. Delta r vector over delta t is equals to r vector as a function of t plus delta t minus r vector as a function of t whole divided by delta t is a vector in the direction of delta r vector, and if the limit of this as delta t tends to 0 exists, it will be a vector along the tangent to the curve at xyz. dr vector by dt is equals to dx by dt into I cap plus dy by dt into j cap plus dz by dt into k cap. If t refers to time, then dr vector by dt is velocity and d square r vector by dt square is the acceleration of point P along the curve. If c is the curve in space and t is equals to s is the arc length from some fixed point on C, then vector t is equals to d r vector by ds is a unit tangent vector to C. The rate at which t vector changes with s, that is dt vector by ds, is the measure of curvature of the curve. Now the rate of change of a unit vector is always perpendicular to that vector. Kinematics. Radius vector from some fixed origin to the position of particle, let it be r vector. Equation of the path of the particle r vector is equals to r vector as a function of t. Velocity and acceleration of the particles are defined as v vector equals to d r vector by dt equals to v t cap. A vector is equals to dv vector divided by dt equals to d square r vector divided by dt square, where t cap is a unit vector along the tangent to the curve. If s be the length of the arc measured from some fixed point of the curve, v is equals to ds by dt. Similarly, a vector is equals to dv vector by dt equals to dv t cap by dt is equals to v d t cap by dt plus dv by dt into d cap is equals to d square s by dt square into t cap plus ds by dt into d t cap by ds into ds by dt equals to d square s by dt square into t cap plus v square into c vector, where c is the curvature of the curve. We have separated the acceleration of a particle moving along a curve into two components, of which one is parallel to the tangent and other is parallel to the curvature c, that is perpendicular to the tangent. The component of the acceleration parallel to the tangent is equal in magnitude to the rate of change of speed and is entirely dependent of what sort of curve the particle is describing. On the other hand, the component of the acceleration normal to the tangent is equal in magnitude to the product of the square of the speed of the particle and the curvature of the curve. But the rate of change of speed in its path has no effect at all on this normal component of the acceleration. The gradient. We now come to vector differential operators which appear when we consider fields. By fields, we imply physical objects that depend on the position of the system or on the point under consideration. They may in addition also depend on the variable time. Relevant examples of fields are temperature in a room, electrostatic potential due to a system of charges, gravitational potential due to a system of masses, charge density in a region of space, and so on. All these are examples of scalar fields where the physical object itself is a scalar quantity. Examples of vector fields are electric, magnetic, and gravitational fields, momentum density, an electromagnetic field, and many more. Now let us first look at a typical vector field V dependent on x, y, and z. We have used coordinates with respect to some Cartesian coordinate system to express the position of the point at which the scalar is being considered. If we consider the neighboring points with coordinates x plus dx, y plus dy, z plus dz, the change in volume V is given by theorem in partial differentiation, that is dV equals to V of x plus dx, y plus dy, z plus dz minus V of x, y, z equals to del V by del x into dx plus del V by del y into dy plus del V by del z into dz. Or it can be written as scalar product of two vectors, that is dV equals to del V by del x into dx plus del V by del y into dy plus del V by del z into dz equals to del V by del x into I cap plus del V by del y into j cap plus del V by del z into k cap dot dx I cap plus dy j cap plus dz k cap is equals to del V dot dr. Del V is equals to del V by del x I cap plus del V by del y j cap plus del V by del z k cap is a vector quantity, is called the gradient of V or grad V. So now students, let us see the geometrical interpretation of this vector. If theta is the angle between vectors del V and dr vector, then dV is equals to mod of del V into mod of dr vector cos theta. For a given mod of del r vector, the change in V is maximum when theta is equals to 0. Del V points in the direction of maximum increase in V. Further, along the direction dV by mod of dr vector is equals to mod of del V. The magnitude of the gradient gives the rate of increase of the scalar field under discussion. Let us see one example. So where we have to find the gradient of r, the magnitude of the radius vector in terms of coordinates r is equals to under root of x square plus y square plus z square, which tends to del r is equals to del r by del x into I cap plus del r by del y into j cap plus del r by del z into k cap is equals to x by r into I cap plus y by r into j cap plus z by r into k cap equals to r vector divided by r is equals to r vector. The results make sense since the increase in r is maximum along the direction of r. An alternative method make use of dV is equals to del V dot dr vector. For the above cited example, V is equals to r equals to under root of r vector dot r vector, which tends to dV equals to r vector dot dr vector divided by under root of r vector dot r vector, which implies that del V is equals to r vector divided by under root of r vector dot r vector equals to r cap. So let us see another example where V is equals to r vector cross a vector dot r vector cross b vector is equals to r vector dot r vector into a vector dot b vector minus r vector dot a vector into r vector dot b vector. dV is equals to 2 into dr vector dot r vector into a vector dot b vector minus dr vector dot a vector into r vector dot b vector minus r vector dot a vector into dr vector dot b vector equals to del V dot dr vector. This implies that del of V is equals to 2 into a dot b r vector minus a vector into r vector dot b vector minus b vector into r vector dot a vector is equals to b vector cross r vector cross a vector plus a vector cross r vector cross b vector. Which of these two methods for computing del V should be applied in a particular case depends entirely upon their relative ease of execution in that case. The second method is independent of the coordinate axis and may seem to be preferable. It is also usually shorter when the function can be expressed in terms of r. But When the function cannot be so expressed, the former method is much more convenient.
Students, now let us study the importance of operator del. Suppose T xyz is the temperature at the point xyz of a heated body. The direction of heat flow is the one in which the temperature decreases most rapidly. The direction of most rapid increase of temperature is given by del T. Hence, the flow of heat F is equals to minus K del T. Let V be the electrostatic potential at a point due to a charged body. The force acting on a unit charge at a given point xyz due to this body is in the direction in which potential decreases most rapidly. Hence, F is equals to minus del V. The operator delta as a vector. The gradient of a scalar formally looks like a vector multiplying a scalar, that is del V is equals to I cap into del by del x plus j cap into del by del y plus k cap into del by del z into V. The term in the bracket is called del.
This quantity has the appearance of a vector, but it is not a vector. In fact, by itself it has no meaningless until it operates on a function of coordinates. The operation is not one of the multiplication but differentiation. Hence, del may be regarded as a vector operator which on acting on a scalar field produces a vector quantity, and that is known as the gradient. However, for all practical purposes, this quantity may be regarded as a vector. It acts like a vector in all vector relations.
For example, del u plus v is equals to del u plus del v, and del uv is equals to del u into v plus u into del v. The directional derivative. If a vector represents any vector, constant or otherwise, the formal combination a vector dot del vector is equals to ax I cap plus ay j cap plus az k cap dot product with I cap del by del x plus j cap del by del y plus k cap del by del z is equals to ax into del by del x plus ay into del by del y plus az into del by del z is a scalar differential operator. The component a vector dot del vector into v is equals to ax into del v by del x plus ay into del v by del y plus az into del v by del z. If a vector is some unit vector, then a cap dot del vector into v is equals to ax del v by del x plus ay del v by del y plus az del v by del z, where ax, ay, az refers to directional cosines of the line a cap. Consequently, a cap dot del into v is the directional derivative of v in the direction of a vector. A cap dot del into v is equals to del v by del s is equals to ax del v by del x plus ay del v by del y plus az del v by del z. In particular, if a cap represents the unit vector along the normal to the surface of constant v, then nx, ny, nz are the direction cosines of the unit vector. So, n cap dot del vector into v is equals to del v by del n is equals to nx del v by del x plus ny del v by del y plus nz del v by del z is the normal derivative of v. Though a cap dot del vector into v is equals to a cap dot del vector into v, the two may be interpreted differently.
Now students, let us study the divergence, curl and the Laplacian operators. As we have seen, the operator del can be regarded as a vector for all practical purposes. The three operations of multiplication that we defined earlier can be just as well be applied to this vector operator. Thus, we have this is similar to the cross or vector product of two vectors. The caution about the order of two vectors applied to this case as well. Del phi, gradient of the scalar phi. This we have already introduced earlier and is akin to multiplication of a vector by a scalar. However, the order of two factors is important here, so phi del is still an operator. Del dot A vector, divergence of a vector field A. This is also often written as divergence A vector, that is div A vector, and is pronounced as del dot A. This is akin to a dot or a scalar product of two vectors. Again, it must be emphasized that the order of the vectors is important. Obviously, A dot del is not the same as del dot A. Del cross A vector, curl of a vector field A, also written as curl A, and is pronounced as del cross A.
The divergence. In the Cartesian coordinate system, the divergence of a vector takes the form del dot A vector is equals to I cap into del by del x plus j cap into del by del y plus k cap into del by del z dot product with ax I cap plus ay j cap plus az k cap is equals to del ax by del x plus del ay by del y plus del az by del z, which is like the dot product divergence of a vector is a scalar quantity.
The name divergence is appropriate for this quantity as del dot A vector is a measure of how the vector field spreads or flows out. To understand the physical meaning of the divergence, let us endure a vector with the property of a flow of a fluid substance or an electric or magnetic field. So a vector denotes at each point flow of some fluid. Then del dot A vector represents at every point the rate of flow of fluid per unit volume per unit time. Now consider a small cube of matter with the edges of length dx, dy, dz as shown in the diagram.
Consider a small cube of matter with edges of length dx, dy, dz as shown in the figure. So A vector is equals to Ax as a function of xyz into I cap plus Ay as a function of xyz into j cap plus Az as a function of xyz into k cap. Now consider the small amount of fluid that passes through the faces of the cube parallel to the x-axis. The flux through the left face is minus I cap dot A vector as a function of xyz into dy dz, and through the right hand face is I cap dot A vector as a function of x plus dx y z into dy dz, which is equals to I cap dot A vector as function of xyz plus del A vector by del x into dx whole multiplied with dy dz. Hence the net flux faces parallel to the axis is I cap dot A vector xyz plus del A vector by del x dx into dy dz plus minus I cap dot A vector xyz into dy dz equals to I cap dot del A vector by del x into dx dy dz equals to del ax by del x dx dy dz. The total outward flux from the cube is therefore I cap dot del A vector by del x plus j cap dot del A vector by del y plus k cap dot del A vector by del z whole into dx dy dz, which is equals del dot A vector represents the increase in density. In case the fluid is incompressible, then del dot A vector is equals to 0, which is also called as hydrodynamic equation. A vector whose divergence is 0 is called solenoidal. For example, let us find out the divergence of the position vector del dot r vector is equals to del x by del x plus del y by del y plus del z by del z is equals to 3. For example, divergence of the vector r vector divided by r cube del dot r vector by r cube is equals to del by del x by r cube plus del by del y of y by r cube plus del by del z of z by r cube is equals to 0. The divergence of r vector by r cube is 0, though the function seems to be diverging everywhere as the gradient is not defined at the origin, because del dot r vector by r cube is not defined at the origin where it is infinity. Let us see the curl. In Cartesian coordinates, del cross a vector is equals to mod of I cap, j cap, k cap, del by del x, del by del y, del by del z, ax, ay, az is equals to del az by del y minus del ay by del z into I cap plus del ax by del z minus del az by del x into j cap plus del ay by del x minus del ax by del y into k cap. This is the counterpart of the cross product of two vectors. Curl of A is the vector quantity as given above. The name curl to this operator was given by Maxwell. As the name indicates, it is the measure of how much the vector curls around and is related to the angular velocity. However, the interpretation in this case is a little more subtle than the case of divergence. A vector field whose curl is 0 is called irrotational. Let us see two examples here. First, curl of radius vector del cross r vector is equals to del z by del y minus del y by del z into I cap plus del x by del z minus del z by del x into j cap plus del y by del x minus del x by del y into k cap is equals to 0. Here the radius vector is everywhere radially outward. It diverges, that is del dot a vector is equals to 3, but it does not curl. Second example, a is equals to y I cap minus x j cap and a vector is equals to y I cap. As we move to the neighboring point, the first vector curls around continuously but does not diverge. However, the second vector increases in magnitude with y but is positive for positive y or negative for negative y. In both cases, curl is expected to be non-zero but divergence is expected to be 0. Indeed, del dot y I cap minus x j cap is equals to del dot y I cap is equals to 0. Del cross y I cap minus x j cap is equals to minus 2 k cap and del cross y I cap is equals to minus k cap. So now let us see the product rules. Since formally the del operator acts both as a differential operator as well as vector, the product rules when gradient, divergence and curl of more than one scalar or vector functions is involved can be obtained by applying the appropriate rules for the two. Some of the important identities involving scalar fields u and v and vector fields a and b are del uv is equals to u del v plus v del u. Del of a vector dot b vector is equals to a vector cross del cross b vector plus b vector cross del cross a vector plus a vector dot del into b vector plus b vector dot del into a vector. Del dot u into a vector is equals to u into del dot a vector plus a vector dot del into u. Del dot a vector cross b vector is equals to b vector dot del cross a vector minus a vector dot del cross b vector. Similarly, del cross u a vector is equals to u into del cross a vector minus a vector cross del into u, and del cross a vector cross b vector is equals to b vector dot del into a vector minus a vector dot del into b vector plus a vector into del vector dot b vector minus b vector into del dot a vector. Though some of these identities can be proved by direct vector method, the simplest and the straightforward method is to be appeal to tensor notation and the summation convention that will be introduced in a later module on tensors.
Now let us see the Laplacian. Del is a first order differential operator and consequently gradient, divergence and curl are the first order derivatives. By applying this operator once again, we can obtain second order derivative. Various possibilities are gradient of divergence, that is del into del dot A vector, divergence of a gradient, that is del dot del U, divergence of curl, that is del dot del cross A vector, curl of a gradient, del cross del U, and curl of a curl, that is del cross A vector.
The first, gradient of divergence, does not occur very often in physics or engineering. The second, divergence of gradient on expanding gives del dot del u is equals to I cap into del by del x plus j cap into del by del y plus k cap into del by del z dot product with del u by del x into I cap plus del u by del y into j cap plus del u by del z into k cap is equals to del square u by del x square plus del square u by del y square plus del square u by del z square can be equal to del square u, and it is also known as Laplacian of u. Laplacian of a scalar is a scalar. The third and fourth second derivatives are both 0. Finally, the fifth is a combination of first two, that is del cross A vector is equals to del into del dot A vector minus del square A vector. Thus, essentially, we have only two second derivatives. The only one of importance, however, is the Laplacian.
Now let us summarize what we have learnt in this module. We began with a discussion of simple differentiation of vector with respect to a scalar like time. Next, we have given a description of a curve in space and discussed the concept of curvature and radius of curvature. Then we have described kinematics of motion of a particle in vector form. The most central concept of derivative of a vector with respect to space coordinates, the gradient, has been introduced, and the geometrical interpretation of the gradient is also discussed. Next, we have described the various properties of gradient both as a differential operator and as a vector. We have also studied the related differential operator of divergence and curls of a vector and the Laplacian operator. Finally, we have written down the product rule when the gradient, divergence and curl of more than one scalar or vector function is involved. Thank you.